name is Sebastian. I'm from Germany, from Munich. I'm a Java consultant, trainer, conference speaker, whatever you call it. And I'm also, well, heavily involved in all kind of Java and all kind of Java enterprise. I'm participating in the JCP. I'm an expert group member for CQRS and JCP for Java EE8. And I'm also a so-called Java champion, and last one's double rockstar speaker for the Java 1 conference. So a lot of Java involved here. And yeah, today the session about CQRS. So normally I would love to live code everything, but as it will turn out, it's not that easy to cover that in 50 minutes. So it's gonna be a lot about the concepts, what I want to show you today first, about the concepts of event-driven applications, of distributed systems, and finally of CQRS, and most important, why do we need this? Why should we care as developers, right? So let's start with enterprise systems, like in a normal way. So for probably since 1,000 years, we've been built enterprise systems in a CRUD-based way, right? We're using relational databases and some, well, atomic transactions, ACID transactions, right? And the question, what is wrong with that? Well, first of all, there's nothing wrong with this, but once we scale more, we go into distributed systems, and we think about the way how we build this, then we see a few shortcomings. First of all, if we store our data in a CRUD-based way, then we're basically storing the status quo, the current state of our system in a database, right? Once you change something to the system, you have a new status quo. You have a new state. And first of all, if you think about that, then of course you lose all the context, you lose all the history, right? Once you have a new state, then everything is forgotten what has been there before, unless it's locked externally, something like that. This can cause some problems, but more about that later. And then most important, since everything is just stored in that state right now, and you have concurrent transactions, concurrent access from users, then you have to deal with all these competing transactions, right? Two users want to change something at the same time and access your system, and so on and so forth. And in order to be consistent, that's what the C in ACID stands for, you have to somehow deal with these transactions. And that more or less means you have to synchronize on some level at some point, normally in the database. And that means, sooner or later, because of that, your system cannot scale forever. CRUD-based systems are somewhat monolithic. Even if you have several application servers accessing one database, then you will have one bottleneck if you try to scale forever. And mostly that's also not a problem, not at least in the typical enterprise applications we tend to run, unless you are called Google or Amazon or something like that. But yeah, more about that later on. And now, when it comes to CQRS, what I want to talk about, I would say there are two basic motivations that drive us to this CQRS model. One is event sourcing, and the other thing is event-driven applications. First of all, about event sourcing. So what is that? So event sourcing doesn't have to be really applied in a modern way. Event-sourced applications have been around for at least 20 years or more. What it means, you're storing not the current state of the application as is, rather than you store everything that comes into your system in an atomic way. So every changes that happens to come into your system will be stored as, well, atomic events. The most famous example are money transactions in a bank account, right? You start from 0 and then you get some money in, you get some deposit, you get some withdrawals, plus 100 euros, minus, and so on and so forth. And in order to calculate the current balance on your account, you basically, well, start from 0 and apply all these things, plus, minus, and so on and so forth. And then you get the current balance. But you don't really store that, or you don't have to store that current balance. You're basically storing all the atomic transactions. And by doing so, you naturally have the full history and the context what's going on in your system, right? If you want to, well, see how your system got into that current state, well, you just look at the history, and that's naturally part of your system. If you're looking at your bank account, sometimes you're interested in the current balance, but mostly you're interested in the actual transactions, right? If everything there is valid, for example. And that enables a couple of things. Well, besides the fact that we can see the full history, we can, for example, do some statistics on them later on if we want to calculate this and that, or use that for testing later on. This is actually the perfect basis for end-to-end tests, right? Because we see everything that happened to our system in the last 2 years, and we can use that for further tests, for example. And it's also somewhat what I would call proof of future use cases. For example, if your manager comes and, because manager do these kind of things, and asks you, by the way, this system that has been running for 2 years, how many users did sign up on a Monday? And now, fair enough, you could as a developer say, well, sorry, that was never specified, I can't tell you. But if you're doing, and if you have a CRUD-based system, then you can tell, right? Because you just have the current state, the current list of users or something like that. But in an event source systems, actually you can, because you have all these user sign-up events still lying around. You look at the timestamp and then just calculate what's needed. So you have everything that happened to your system, which is a really benefit. However, now to the second motivation that enables CQRS, and this is event-driven applications. And now about event-driven architectures, why do we need that? Well, once we're doing what is called microservices, once we want to distribute, or we have to distribute our systems, and when there are several systems involved, then, well, why do we need that? Basically, we need that because we can't scale doing a monolithic approach. Because what would that mean? If we want to be consistent, having everything spanned in one transactions, then we have to do distributed transactions, right? If you don't know what distributed transactions are, that's good, because don't do them. This will not work, this will not scale. Distributed transactions basically means we will take several systems and lock all of them down at the same time until our transaction is finally committed. And of course, this creates a huge bottleneck. It doesn't work. So in order to solve that, you can apply these event-driven architectures. And before I tell about this, how it works, let me tell you an example from the real world. Let me tell you a story. So, because then you will see that it's actually very related to the real world to do event-driven architectures. For example, you go into a restaurant and you want to order something to eat, a salad or a paella. And then you go in and you tell the waiter, quiero uno plato de paella, por favor. Something like that. Thanks. And of course, the waiter will answer, sí, claro, right? And then you ordered the plate of paella, and the waiter accepted your order. However, this does not mean that you get your plate of paella, because a lot of things could go wrong. Although the waiter accepted your order, the waiter may then go to the chef and orders that meal, and then actually they get told, oh no, we just ran out of paella and we don't have it anymore. So what happens, the waiter will come back to you and say, well, sorry, we're out of paella. And then you either order something else or angrily leave the restaurant or whatever. But you see, this is not consistent, of course. Because what you would expect building an enterprise system is you go there, you order the plate of paella, and then something happens in a synchronous way, and then you end up with your plate or an error. But the real world doesn't work like that, right? A lot of things could go wrong, and it's fully asynchronous. It's fully event-driven, if you like. Because what happens, first of all, you need this collaboration, since it just doesn't work to lock down the whole restaurant and wait synchronously until everything is finished and everything is prepared for your paella, that you either get it or get an immediate error. And also, well, you have to think about all these things and compensate for exception handling, for errors, because these errors will happen anyway. And also you're trusting outdated information, right? In the morning, the waiter has been told there is enough paella, then he knows then they run out of paella. Maybe now the next customer comes in and orders also that dish, and then he gets told that we're out of paella, but at that very second, the delivery truck comes and brings him new ingredients, right? So you're dealing with outdated information all the time. And what you're doing in an event-driven way, that you're aware of that problem, because we're building applications for the real world, and you build that in immediately. So what happens if you have several systems involved, and this is this is the basic for that, you have to have distributed systems in order that it even makes sense to build event-driven architectures. And then you're just communicating via these events. And by doing so, you're splitting up these transactions, right? Because rather than ordering the dish and waiting in a synchronous way, I order the dish, and then I can go to restroom, I can check my phone, and later on I get a result. Either it's possible and I get the dish, or I get an excuse. But it's done fully asynchronous. And there are still transactions, but they are split it up. And by doing so, we can scale, of course, much more, but more about that later. And what that now means in software, let me give you another example. Let's do some coffee. Like a restaurant, let's say we go to some nice coffee shop, and you have basically 3 systems involved, right? So have an order system with the order management running there. You have a beans, which is basically a coffee bean storage, right? So let's assume if you want to order a coffee, then you have to check whether there are a lot of enough coffee beans still available. And then you have the barista system, that guy who's sleeping in the corner until some order comes in and prepares our coffee. So what happens now? We have this client access, order some coffee, and we have these 3 systems involved. And now, let's assume you go to the order system, of course, to order the coffee, and in order to accept it or not, you have to check against the bean system whether there are enough beans available, right? And if you want to do this in a synchronous way, then of course you would have to do distributed transactions, go to the second system in a synchronous way, wait until the response, and then store it or not. Bad idea, because it doesn't scale. This would be a distributed transaction. In an event-driven way, what you do, the client comes in, says order coffee, you say sure. And what you do, you store an event, order has been placed. Order placed in your order system. And that's it. It doesn't mean order accepted, that it's somewhat possible or not, it just means order placed. And all these events, again, are immutable, and very important, they happened in the past. So they are a fact, they can't be changed. And no matter whether that's possible to get the coffee or not, the order has been placed. And now what happens, that the other systems are somewhat interested in that event. Oh, and by the way, the client returned, so that's gone. Order placed, yeah, I got your order, let's see if it's possible, we will come back later. Now the other systems are interested in that. And what happens, that for example, the bean system wants to know whether a new order has been placed, because it knows that now it has to validate for the beans. And this is how you distribute your business use case logic to now the second system and say, once that event comes in, we have to validate the beans. So there's a new command, validate beans, and as a result, as I said, you only communicate via events. So either you have an event, fine, or the beans validated, that basically means yes, we have enough beans for your order, or you have another event, sorry, order not possible due to insufficient beans or something. And then again, the order system listens to those events and says, okay, nice, now it's validated. For us, that means the order is accepted. So internally, it issues the command accept order. And then the order will be accepted, so there will be a new event, order accepted. And then the other systems are interested in that, and for example, the barista system now only wakes up and says, okay, now the order is accepted, that means I can actually make it. So, and it goes and makes some coffee, right? And then the coffee brew started, we can update that, in our other systems as well, if we're interested in this. For example, now the beans has to be fetched from the beans system, and so on and so forth. So, right, and finally it will be finished and delivered. But now you get the idea how they are communicating only using these events. And by the way, the barista system in my example, that's basically a timer then at some point says now it's finished and now it's delivered to the customer. And by doing so, you're just communicating via these events. And now the buzzword CQRS. And why is that important? CQRS stands for Command Query Responsibility Segregation. 3 long words. If you put all of that together into one word, that could be German, right? That's what we Germans do. And it basically means separating the write side from the read side in a system, so that you have commands and events. And what I just showed, you are issuing commands in the beginning, and then you have some events resulting out of that. And only the write side can basically produce events. So why do I need these things like write side and read side? Well, it's about storing the current state. I will show that in a second, why that is important. But basically what you have to do, you have to apply all these events continuously to get the current state of your system. Because you need that, right, if the user wants to read something. And by separating that, you ensure that, well, for the write side, for example, only the write side is allowed to change something, only the write side is allowed to issue new events, and the read side can only return something there. Let me show you this, how that means, what that means for our system. So more nice ASCII art pictures. We basically split up our system into, on the left, a command service and a query service. And they're only communicating by events, what I showed before. So there will be some event store or event hub in the middle, and everybody is just talking to that. And all the systems are independent. That's very important. So what you see with database, that means actually all the systems have either a database, or it could even be just in memory storage to store the current representation. What that means, once a new event gets into the system from somewhere, then everybody who's interested in that will be notified, will get that event, will consume that event, and update its internal storage. All of them individually. And then by updating this internal representation, you have the current state applied, right? Because you're from day one, you're getting all these events, and then you're continuously updating your status quo. So let's do the example for our coffee. What that means, we have, again, a command service and a query service. And for the command service, because it changes something, the place order or order coffee command comes in. So the client goes to that system and wants to place an order. What happens, it can use the internal database to, well, if it does some validation logic that can already be done on the order system without anything else involved, then it can do so. Otherwise, it just places the event. That means it, well, publishes this order placed event to the event hub. And that's the important thing, this has to happen in a reliable way. So this is synchronous, just the publishing of that event, because we want to make sure that the event really is in our system once we tell the client, yes, accepted, we accepted your order placement. And then the client returns, and that's it. But that's quite important, it has to be sure that this event is there. And now what happens, the client can come back later now. All these events are then well, published to the consumers who are interested in that. And one consumer is, for example, the query service, who updates its internal storage, its internal representation. And once the client comes back later and asks, of course, the query service, because now it wants to read something, to give it the current representation of the coffee order, then it just returns its internal representation that has been updated from all these events. Any questions so far? Okay, good. The same is true for command service. So also the command service, if it has to, will consume events and update its internal representation. And also there will be an event handler who then will fire, well, subsequent commands if needed. So for example, you get the order placed coffee event into your system, and then the next beans system goes and tells you, okay, now we have to validate the beans, for example. And that will happen in the event handler, because the event handler gets the order placed event that was issued from the other system. And this is how you communicate, and this is how you drive that forward, the whole process. And, well, by doing so, first of all, you can scale independently in two ways. Each and every, well, bounded context system can scale. So you can have a lot of order systems, you can have a lot of beans and barista systems if you need to, without affecting the other ones, right? Because they are totally independent. And even more interesting, you can scale the write side from the read side independently. Because what happens, naturally, if we have a web-based application, then typically the number of reads highly outperform the number of writes, right? We're constantly reading something, and once in a while we change something to the system. So what you could basically do, you can scale up just the read side to have that in a lot of in a high number of instances, and all of them get updated once a new event comes in, and the client can go to a lot of all these systems. They're highly distributed, and you just have a couple of write systems, just a couple of command service systems, because you're not writing that frequently, for example, and this gives you that flexibility. Also, you can optimize each side independently, right? If for some reason it makes sense to use a relational database on that system and a NoSQL database just to store the current representation, then you can do so, because they're just communicating over these events. There are no dependencies whatsoever. And also a nice benefit, you get failover capability for the read side. So basically, if your event hub breaks down and you're not able to write anything anymore into your system, you still can read, because you're caching basically everything in all these systems, right? You can't change anything, but at least you can read. And in a traditional CRUD-based application, if the database breaks down, then you can't do anything anymore, right? Normally. So let's finally talk about a little bit about code, and have some demo also. So what I did, I created, to showcase that, I created this, what you just saw in the example, as a so-called scalable coffee shop, consisting of 3 systems, like a barista system, beans, and order system. And what that is, this is a Java EE application, or more precisely 3 applications that implement the CQRS approach using Apache Kafka. So I have Apache Kafka as an event hub, or more or less event store, that is responsible to distribute all these events, and I have 3 applications accessing this. And let's start to dive a little bit into code. So as I said, I would love to live code everything for use, or what I'm normally doing but this is actually one of the drawbacks of that approach, and I will talk about that at the end. That is quite a lot of code compared to a CRUD-based way. So you have to write a lot of classes, all these events classes. You have to write more functionality to do all this event handling, and so on and so forth. So it definitely has some drawbacks. But let's start from the beginning, just to give you an idea how these systems work. So also for simplicity, I put in both the write side and the read side into one application. But from the code level, they're totally separated. So you could equally split them up into several applications if you need to. And basically what that means, for example, if we want to place an order, right? We want to do so over HTTP, let's say, so we are communicating via REST. And what that means in Java EE is probably that you're including JXRS, right? And you have a JXRS endpoint that we call, for example, orders resource. And what it is, you can, well, use the path orders to, and here it's still together, the write side and read side, to create or read coffee orders. But then you will see I have two services, command service and a query service, and then that they are split up. So what happens if you want to create a new coffee order, then of course you're posting something to the system, and you're posting, let's say, something in JSON, and after, well, choosing some random ID, you basically go to the command service and say, place new order with that order info. And you see this method is void, of course. Well, CQRS applied. You can just call that method. And what happens, either that method is, well, will be executed successfully, or you get some exception, but you don't get anything returned, right? So then we can go to an event producer. I will show that in a second. This will basically produce and publish the event to Apache Kafka. And once that returns successfully, we know that the event has been placed and that the event is in the system. And then we can come back and tell the client, yeah, 202 accepted, thanks, come back later. And by the way, here's the location where you can ask for the order later on. Similar thing to the read side. If you want to get an order, you ask for a specific order ID that you have been given to once you created that, and now you can read it, of course, using the query service to get the order. And what it does, it, well, goes to its representation, the database, and returns that order that has been, well, constructed using all these events that came into the system. And what that means for us, this database is here just in memory, because I want to showcase a couple of things there. And you're basically using some hash map to return this. And that's basically it. Of course, this runs really fast, since we are just returning something from memory. And also, if you include, for example, a relational database, then this would be the place to do so. It will also run fast because nothing else is involved. It's just a database lookup with an ID, and then you're just returning the current representation, right? And what happens, so what we're doing, and I will show this in a second, how that's integrated. Now, once events come into a system, events that we're interested in, for example, everything that happens to orders, these events are observed by a CDI. As I said, I'm using Java EE, and Java EE naturally comes with some eventing mechanism, CDI events, and these are observed here in all these methods and then applied to our current state. In domain-driven design speak, this would be an aggregate, right? And what we're doing, we're just applying all these things to, for example, accept new orders or cancel or start them and so on and so forth, and apply them into the representation. Once a client comes and wants to read, we will just return that here. And that's basically it. And now I just want to briefly talk about how we integrate Apache Kafka. If you're interested in that, I can show you a couple of pointers later on. But what we're basically doing, we will have some event consumer that is basically firing CDI events. So this comes and consumes with a so-called Kafka consumer group, consumes the events, and once they come, they will get fired. And in order to integrate that, well, you have to do something like this. You will write in a consumer, and it will listen until it's basically stopped. And in order to be safe in a Java EE environment, you have to tell it once the application server will be shut down. So you will have some pre-destroyed annotated method that will then stop the consumer, who stops this this infinite loop, and so on and so forth. Well, long story, what basically happens, once events comes into our systems, we want to throw CDI events. And this is a very nice way of integrating it, because then you can, well, decouple all the rest of your application from that integration, since then you're using first-class citizens of Java EE CDI events, and you're just communicating using these events or the event publisher if you want to, on the command server side, store something into Kafka, right? And actually a similar thing is there for the event handler. So there is an event handler involved that will then, for example, once the beans have been validated, issue new commands. So what it does, it also listens to these CDI events that will be fired using another consumer group, and then it basically goes to the command service, of course, because it wants to change something, and tells, for example, cancel order once we know that the beans were not available, and so on and so forth. So this listens to the events from the outside, from the other systems, and then does this event handling. Basically, it does the further processing of all this. And now some live demo. So what I have here, I have our 3 systems involved, the order system, bean system, and barista system. These are just 3 shells. And what I'm doing, I will be running 3 Java EE applications, of course, in an application server in a Docker container. So that means I will have 3 independent Docker containers, or more if I like to. By the way, the nice story is that it integrates well with Java EE and Docker, because we can tell our application server, I will have Whitefly in my case, I can show you the Docker file, that it basically uses, some private base image using Whitefly and Kafka. So you can have a very nice thin WAR file approach that only contains the classes we compile, and everything else is provided, right? So you can throw that into, for example, the auto deployment directory, and it will know that the application server does all the implementation plus Kafka client API for us. And in order to do so, we built everything. I will use Maven here, Maven clean package, to build that into a thin WAR file. Then we Docker built this, of course, into the order system here, and we run the Docker container by exposing this port. And this will build this orders WAR file, and the same is true for the beans and the barista system as well, because these are really independent systems. And what happens then, all these systems will go up, and then it tries to connect to Kafka, and that's it. And now we have all these systems involved, so you can open up another shell and basically ask for the orders, right? Orders. So what we can do, for example, we can get 8001 that ports to the order system, and of course method not allowed, because we can just post something here. So let's do this. Let's post a new coffee. I will use just curl. So what we're basically doing, we're posting a new JSON because we want to order some coffee type espresso from beans origin Colombia, right? And what happens, we put that into the system and to accept it, right? Even though we don't know if it's possible or not, but it will tell us, okay, thanks, come back later, and it will give us the location with that ID that we can, of course, query to our coffee. And you will see canceled. Why canceled? Because immediately we put it into the system. The second system, as I told you, will try to validate the beans, and actually the beans system will tell you, oh, beans not available. Well, because how it works, the beans system also has a storage, and we have to store beans first. So although it was accepted in the first place, and now you see these eventual consistency, your order has immediately been canceled. So what we're doing now, beans, you will see empty JSON object. We have no beans in the system. Let's post some beans. Where is my nicely prepared curl statement? Otherwise this takes a while. Localhost, this was the system 02. We will post some JSON to that system just to create some beans, right? What happens for no content, we immediately accepted these coffee beans, and then using the log file you will see, oh, beans stored, there's an event here, and if we ask again, you will see that now we have 10 beans of this type. So we can order 10 coffee. And now we can basically reorder this. So we can issue a new order now. And again, it will tell us to accept it. Because what happens, it placed the order, it fired that event to Apache Kafka, and now it's, well, accepted. Why is it accepted? Because, so placed would be the first status, and then accepted because it will tell us here beans order accepted, and somewhere else, yeah, order beans validated. So the second system, the bean system, will now say we have enough beans and fire that. And basically what happens afterwards, that this, oh, yeah, this coffee delivered. Did I use the wrong? I think so. Let's do this again. It's accepted, but actually should be delivered. That's very interesting. As you can see, the event was fired here, but I think there is something wrong. Yeah. Yeah, that's very interesting and a good thing for the live demo. So what you have to take care of using event-driven approach, you just don't know when the events arrive, right? Because this is not synchronous. And now apparently there's something wrong because the network changed, and what it does then, Kafka will actually reapply all these events later on. So this is not synchronous, right? So I was firing that event, and then actually the barista system on the right already told us, yes, I prepared that coffee and so on and so forth, and fired that event as well. And this event apparently is not has not been published yet into all the other system. And then, of course, your coffee is not updated yet. And this is actually, this is just per se eventual consistency, right? And this is also what happens to all the big systems out there, right? If you look at Facebook, if you look at Twitter, it's highly inconsistent. If you tweet something and you refresh, you may not see your tweet immediately, right? And if you tweet something and your colleague refreshes, they might not see your tweet immediately because before all these events get distributed. And this is, no. You saw that? Now the event arrived. I think there was just some weird network issue and timeout. Normally that would be done immediately, just like in the beginning. So what we can do now, you will see that now the status has been updated. Yeah, thanks Kafka for screwing up my demo by being so slow. But this is now the natural outcome. So what happened? The barista system immediately responded and did all this eventing thing, and now it took a while until the other systems actually knew about that, and until the order system updated that. That means the client immediately got the coffee, and the order system, because it's so slow network, tells us, oh, it's still preparing until, I actually have my coffee already. And this is what happens to the real world as well, right? Highly inconsistent, if you think about it. But this is actually what happens. And this is how the systems communicate. And now, one last thing that I want to show you. So what I did just now, I killed the order system. Why? Because I like to. But now all the orders should be gone, right? Because they're in memory. But what actually happens is that this system can reconnect to Kafka, and this is now how you manage all these events. You can tell Kafka, based on the what is so-called Kafka consumer groups, please re-deliver all the events. And this is actually what will happen once I fire up the system newly, or a new system, another one, that will go to Kafka and get all these events re-delivered. So that means everything that happened from day one can be re-delivered, so you're in the current state. So this system again, now the order system is up again, can tell us about the delivered coffee order. Although this is stored just in memory. And this is now being reapplied using that old event that has been re-delivered with the same information and so on and so forth. So this is the nice story about that. Now what you can do with this, you can basically go to, for example, where is you can go to this bean and change some business logic here. If you find some bug, or if you want to enhance something here, for example, I want to add some statistics, right? Please calculate the average time that it takes to brew the coffee or something like that. And what you can do, you can insert some code here, and you can just deploy your application. And then you say, for example, throw away all this current state, what naturally happens if you're just in memory. All the events get reapplied, and then all this process gets recalculated as if your functionality has been there from day one, because it's just being recalculated right now. And for example, if you use some statistics here, or if I just would log all the events, then you will see the same outcome as if that functionality has been there from day one. So this is a very nice approach of fixing something or changing something, and then let's say, okay, let's rewind to the past and just reapply this. And you can do so because these events are immutable. So they can't be changed anyway. They happened in the past, and you can just recalculate the current status quo, right? Same on your bank account. The transactions in the past, you can't change them, right? You can do some compensating transactions in the future, but you cannot delete transactions. And the same here. There is no delete in events. You can say customer deleted, that's an event, but there will be some time in the middle where the customer is there, and afterwards you apply the customer deleted event, then it's gone. Okay, that's fine. But you can go to any random point in time and calculate the current state, and it's valid, right? So in the same way here, you can reapply and redeploy your application, reapply all the events, and say, I will, for example, now use some different functionality to calculate the current status quo if you change something, and then you will see the outcome. But these events can change in the past. And this is a very interesting way, I think. And of course, if you would introduce some persistent snapshot, what it's called, you would do so here as well. Because if you do so in production, this is not the best way, because what happens once your system has been running for 2 years, you have millions of events, and once you start up, all these get redelivered, and that takes some time to calculate, right? So once in a while, you want to have some persistent snapshot, basically, or just by storing the current status quo in your database, and then just tell Kafka, please give me all the new events that I haven't committed to yet. And this is what you can do. So now, one last thing about CQRS. So do you have to do CQRS? No, of course not. When should you consider it? If you're doing distributed systems, and only if you're doing distributed systems. And also for microservices and the whole thing being distributed, there has to be a reason. Don't do microservices because it's cool right now, right? You have to have a reason first to do so. If you can stay with non-monolithic, maybe CRUD-based application, that's fine, that's good actually, because that's simpler. You see now that it's actually a lot of code required to do all these handling of these events as compared to traditional CRUD-based applications, right? So this is a very important point. If you can avoid it, then of course avoid it, because it's much simpler to do a monolithic application that still scales for what you need, for your demand, then this is actually better. If you want to have the benefits of event sourcing with all the history and all that, you can still do so. You can definitely do event source system without being distributed, without being event-driven over the applications, right? You can just store all these events in a consistent way, in a CRUD-based way in your database. Actually, that's how databases work internally as well. And then you're fine. You have all these benefits, and you don't need to deal with event-driven applications. So that was a very quick run over that implementation, also that application that you can have a look into using that GitHub repo. Also, I recorded a video course that's available for free about that topic and more, where I will show this coffee demo and so on and so forth. You can check out on my blog on my website. So there you have more time to listen to the topics, more than 50 minutes. And do you have any questions left now? about, well, being distributed, about event-driven applications, about CQRS or Kafka or Java EE in general? Yes, please.
Hi. If at some point in the future the event structure changes, then how do you read all the past events that doesn't fit the new structure, or how do you handle that?
Yeah, this is a good question. What if the event structure changes? I would argue it cannot happen, right? It shouldn't change. Why should it change? That would mean that's actually a business question rather than a technical one. If you got some order into your system, then you had some information at that point when the client ordered, and that should be sufficient, right? Otherwise, you had a bug in your business use case. And if you use all this information, then you should be able to deal with that. The same is actually true for API changes. If you want to change or version your REST API, I would argue don't do it, because what happens to the old clients, what happens to before, it was all that wrong before, right? Actually, that would be a big problem, basically, because, as I said, these events can be redelivered and all that. But the events are there. They're, in my case, stored in Kafka. So you're not creating new events. These are immutable. And this is a much bigger question, well, a theoretical question. What does that actually mean if you want to change the event? First of all, why should you change it? And what happened to everything that already happened in the past? Do you want to change that as well? And, you know, and I thought about that, and once you think about it, you can't really answer that other than from a business use case. Because if you think about that, and now you could ask your manager, now what do we do different? Like we did in the past, like we just did right now. So actually that should not happen. And I say should not from a business perspective. From a technical one, if for some reason you would have to, well, then you would have to actually change everything and, well, take all the systems down, obviously, and, well, basically deleting everything and reapply it externally in some way, because then the events here in Kafka, for example, are invalid, right? Which also doesn't make sense if you think about it. So this actually should not happen, at least for the event structure. But a very important question, yes. Any other questions? Yes.
So to stick to our example, what happens if you have several instances of the barista, for example? Do you have the option to consume an event?
Yes, that's a very good point. I skipped that topic shortly. What is very important, every system gets all the events that are used to update their internal representation, right? But only one, and I mean exactly one system, should get the events to process and trigger further commands, right? Once you have the order placed, a command coming in, then only one bean instance, if you have several of them, should actually validate, right? Otherwise you have 3 resulting events if you do 3 of these instances as well, and this would not work. So what you have to think about, and this is actually a very important point, that you have one event handler that consumes all these events reliably. What you can do, and what I did using Kafka, is Kafka uses so-called consumer groups, and what Kafka guarantees is that if you configure it that way, that exactly one consumer per consumer group will get that event reliably. So what you're doing, basically, you have one consumer group per instance for the updating side, so that all the updated internal representations get updated per instance, but you only globally have one, what I call event handler consumer group, that takes care of, I take that event and I issue new commands based from that. And only one system does that reliably. And that's a very important point. And this is very true. And also, if you redeploy your application, then you should connect to the same consumer group, for example, if you use that approach, so you don't get these events redistributed, right? Because then what would happen if you fired up the application again, then a new order, a completely new order would be drawn out of that, and that also would be wrong, right? So this would change the history. So this is a very important point to think about. These event handlers are a very, very crucial part of that system, yes. Very good question.
Thank you.
Any other questions? Yes, one up there. And that's the last question, otherwise we get thrown out of the room.
If you had an order of 3 or 4 coffees, would you consider that one event or 3 or 4 events?
That highly depends on the business requirements of the business use case. If for some reason it is, for example, always clustered based on your business, whatever you're doing, in one one order is always several drinks, for example, then of course, why not, right? Then you have one event consisting all this information, also in an atomic way, right? Then it would be one event, new order, something, order placed, with all this data as one event. Otherwise, in my approach, it's just one drink per order, but that's just a choice. But it depends on your business. But it should be one atomic event, the one order.
Yeah,
Right.
that was the question more or less.
Yeah, okay.
So
in
it would
your
be
case
okay to produce 4 events with only one command?
Yeah, okay, another good question. Yes, this would be okay if you can produce all these 4 events in an atomic way. So what happens once the client comes in at the very beginning to the first system, to the command service, and issues place order, which in your case consists of 4 drinks, then if for some reason that is more suitable for you, then you can fire 4 events, but reliably, and that would mean transactional 4 events to your event hub, if that is sufficient. But this is a question how you model these events, and it is definitely a good way to be as atomic as possible in terms of your events. So I would argue actually in your case it makes more sense to make this one event, because you have one logical event, or that came into your system, or the place that just happened to contain 4 drinks, right? But this is just a thing I would say about that. But it's not forbidden to throw several events, definitely not. So this is definitely fine. Yeah, so thank you very much for all these questions and all this interest in CQRS, and yeah, muchas gracias, and thanks for your attention.